Welcome back to Basic Electronics. In this lecture, we will look at the principle of superposition. Superposition is very useful in circuit analysis when there are multiple sources in the circuit. We will consider a few examples to illustrate how superposition is applied in practice. Finally, we will look at why superposition works. So let us start. Let us consider a circuit made up of the following elements: resistor, for which V is R times I, voltage controlled voltage source, for which V is alpha times Vc. Vc is a controlling voltage and alpha is a dimensionless constant. Voltage controlled current source, for which I is G times Vc. Vc is again a controlling voltage and G has units of conductance. Current controlled voltage source, for which V is R times Ic. Ic is a controlling current and R has got units of resistance. And finally, current controlled current source, for which I is beta times Ic. Ic is again a controlling current and beta is a dimensionless constant. What is common in all of these equations? They are all linear. That means the quantity on the left, such as V or I, depends on the quantity on the right, such as I here or Vc here, etc., in a linear fashion. And that is why when we have a circuit made up of these elements, the superposition theorem can be applied. In addition to these elements, we have some independent sources, independent DC voltage sources, for which V is V0, just a constant. For example, V0 could be 5 volts or 100 volts. And independent DC current sources, for which I is I0, again a constant. I0 could be 5 milliampere, for example, or 1 ampere. Now, if we have a circuit of this kind with these elements and these sources, such a circuit is linear and we can use superposition to obtain its response when multiple independent sources are involved. And what do we mean by the response of the circuit? What we mean is the currents and voltages in that circuit. The next question is, how do we use superposition? Superposition enables us to consider the independent sources one at a time with the other sources deactivated, compute the desired quantity of interest in each case, such as a current or a voltage, and then get the net result by adding the individual contributions. And the advantage of this procedure is that this procedure is generally simpler than considering all independent sources simultaneously. Alright, now let us address this issue of deactivating an independent source. What do we mean by deactivating an independent current source? Let us look at the equation for a current source right there, I equal to I0. So to deactivate this current source, all we need to do is to make I0 equal to 0. And what does that mean? That means no current is passing through that element. That is, replace the current source with an open circuit. What about deactivating an independent voltage source? Here is the equation for a voltage source, V equal to V0. So we need to make V0 equal to 0. That means we replace the DC voltage source with a short circuit, because a short circuit has no voltage drop or zero voltage drop across it, and therefore we simply need to replace the voltage source with a short circuit. Alright, let us now apply what we have learnt about superposition to this circuit here. Here we have two independent sources. One is a voltage source, 18 volts, and the other is a current source, 3 amperes. And we want to find this current I1 here. So we will take these two sources one at a time. Let us start with the voltage source. So we keep the voltage source and deactivate the current source, and that is our case 1. Keep Vs, deactivate Is. And how do we deactivate the current source? As we saw in the last slide, we need to make the current equal to 0, that is, replace the current source with an open circuit. And in this case, it is easy to calculate I1. It is simply 18 volts divided by 2 plus 4, or 3 amperes. Alright, so that is our case 1. Let us now look at case 2. In case 2, we keep the current source and deactivate the voltage source. So that is our current source, and we have deactivated the voltage source. That means we have made the voltage here equal to 0. That is, replaced the voltage source with a short circuit. And now what is I1 in this case? I1 can be obtained using current division. I1 would be 3 amperes multiplied by 2 ohms divided by 6 ohms. So that is our I1, 3 amperes times 2 by 6, or 1 ampere. And note that we have used these superscripts. This 2 indicates case 2 and this 1 indicates case 1. And now as a final step, we simply add these two quantities, I1 in case 1 and I1 in case 2, to obtain the net value of I1. And that turns out to be 3 plus 1, or 4 amperes. Here is our second example. We have two independent sources here. One is a voltage source, 12 volts, and the other is a current source, 6 amperes. And apart from these two independent sources, we have resistors and we have this dependent source. And what kind of dependent source is this? It's a voltage source, and the voltage here is controlled by this current. If this current is I, then the voltage is 2 times I. So it's a current controlled voltage source. Alright, let us now use superposition to obtain this voltage V here. And how do we go about doing that? We have two independent sources, the voltage source and the current source. We take these two sources one at a time, compute V, and then finally add the two values of V. Here is our case 1. We have kept the voltage source and deactivated the current source. That means replaced it with an open circuit like that. And now let us find V in this case. The important point to note here is that we have left this dependent source as it is. Alright, now how do we solve this circuit? We have a loop here and we can write the KVL equation for this loop, and let us take voltage drop as positive for this purpose. Let us go like this. What is this voltage drop? It's 1 ohms times I, or just I. After that we come across a rise of 12 volts, so that would be minus 12 because it's a rise. Then we come across a voltage drop of 3 times I, so that is plus 3 times I, and then another voltage drop of 2 times I. And when we add all of these terms, we should get 0, like that. We can solve this equation for I. That gives us I equal to 2 ampere, and therefore this voltage V is 2 amperes times 3 ohms, or 6 volts. And note that we have used this superscript 1 here to indicate case 1. Let us now consider the second case, in which we keep the current source and deactivate the voltage source. So here is our current source, and we have deactivated this voltage source. That means we have replaced it with a short circuit. Alright, now how do we obtain I or V in this case? There may be different ways of doing this. One thing that comes to mind is that this current through the 3 ohm resistance is I plus 6, and once we figure that out, we can write a KVL equation for this loop and then obtain I and therefore V. Here is the KVL equation. We are going in this loop starting with this voltage drop 1 ohm times I, or simply I, the first term there, then 6 plus I times 3, that term there, and then finally a voltage drop of 2 times I across the current controlled voltage source, that term there, and all of these terms must add up to 0, and that gives us I equal to minus 3 amperes. This minus sign means that the actual current is flowing in the opposite direction. Once we know this current I, we can find the voltage here as 6 plus I times 3 ohms, that is 6 minus 3 times 3 ohms, or 9 volts. So that is our V with a superscript 2 to indicate case 2. And now the net voltage, this voltage here in the original circuit, can be found simply by adding V1 and V2, and that gives us 6 plus 9 or 15 volts. How do we know if our solution is correct? There are two ways of verifying that. One, we can find the net quantities. The net current here is I equal to 2 minus 3, that is minus 1 ampere. The net voltage we have already found, that is 15 volts. So therefore we know that 15 volts divided by 3 ohms, that is 5 amperes, would go like that. And similarly, we can find the voltage drops across each of these elements. Make sure that KVL is actually satisfied by the net quantities in this loop, and also KCL is satisfied at this node. The second approach for verifying whether our solution is correct or not is to use circuit simulation. Now in this example, and in fact throughout this course, we will use this circuit simulator called Sequel, which has been developed at IIT Bombay over the past few years. And the Sequel circuit file for this particular example is given over here. So we can run this simulation and verify if our results are correct. Here is the URL for the Sequel circuit simulator website, and that URL brings us to the Sequel main page. There is a description about what Sequel is about, what features it offers, and this feature of course is rather important for our purposes. It's a free circuit simulator. You can just download and use it. Then there's a link for Sequel examples. There is a large number of ready-made examples, and you can click here and find out more about that. There is a link for downloading the program, and also there are several video tutorials available about how to use the circuit simulator, the basics of the graphics interface, tutorials, project examples, how to plot graphs, and so on. And these tutorials would be particularly relevant if you're going to make up a new project. On the other hand, if we're going to run an existing project for which the circuit file is already available, then we don't really need to go through all of these video tutorials. In addition, there is the Sequel Users Manual, Part 1 and Part 2. and there is some course material as well. To run an existing circuit file, we note the name of that file. So it is E101 underscore superposition underscore 2, and we can look for this specific project and then run it. Let us see how to do that. The circuit files are placed in various directories depending on which area that circuit belongs to, and so the best way to find where a given circuit file is to search for it. So let us do that. So EE101 superposition 2, this is the file we are looking for, and this file is in a directory called EE101 underscore network under SQL GUI projects. Alright, so let us remember that and open this particular circuit file. So this is the executable file for the SQL GUI, and that is under SQL GUI 2 release. So we double click on that, and then the simulator starts. And now we look for the file of our interest, and as we found earlier, it is in this directory called EE101 network. So let's open that, and that is where that file is. So let's open that file. That is what it looks like. So this is our original circuit. It has got both the voltage source and the current source. This circuit here is the circuit with the voltage source deactivated, and this circuit here is the circuit with the current source deactivated. And notice that there is this fictitious voltage source here called VS0, and that is required because the current through that branch is used by this current controlled voltage source. We have defined some output variables on this right hand side here. In particular, we are interested in this voltage across R2. VR2 here is that voltage in the original circuit. VR2A is that same voltage in this circuit with Vs deactivated, and VR2B is the same voltage in this circuit with Is deactivated. Let us now run the simulation and look at these VR2 values. So that is the table of the output variables, and the net value of V is 15 volts here as we had computed, and the other two values are 9 volts and 6 volts. Instead of constructing these separate circuits with Vs deactivated and Is deactivated, we could just change the parameters in the original circuit to verify our calculations. Let us do that. So let us get rid of this part, and first we will keep the voltage source and deactivate the current source by making the current equal to 0. And now let us run the simulation, and now we find that VR2 is 6 volts as we had computed. Next, let us bring this back to 6 amperes and deactivate the voltage source now, make it 0, and now run the simulation again. And now we get 9 volts once again as we expect. And finally, let us include both of these sources in the circuit. So make Vs equal to 12 volts, Is equal to 6 amperes, and see what happens. And now we get 15 volts as we would expect. Here is our next example. We have two independent voltage sources, Vs1 and Vs2, and we want to find this voltage V1 using superposition. So let us take these two voltage sources one at a time. So case 1, Vs1 alone with Vs2 deactivated, that is replaced with a short circuit. In this case we get V1 by voltage division as the voltage across R2, which is R2 divided by R1 plus R2 times Vs1. So that is our case 1, and we have marked that with this superscript 1 over here. Here is our second case in which we have kept Vs2 but deactivated Vs1, that is replaced it with a short circuit, and in this case V1 is the same as the voltage across R1, and once again using voltage division we have V1 equal to R1 divided by R1 plus R2 times Vs2, like that. And finally our net value of V1 is simply the addition of V1 in case 1 and V1 in case 2, and that gives us this expression over here. This is our next example, and it is essentially the same as our previous example, except we are going to treat it a little differently, and that is by designating one of the nodes, this node, as the reference node or the ground node. And this is indeed a common practice in electronic circuits. It makes things much more convenient, as we will see. So this node voltage is 0 volts because that is the reference node. With respect to that node voltage, the voltage at this node would be Vs1, the voltage at this node would be V1, and the voltage at this node would be Vs2. So we can redraw this circuit in which we don't bother to show explicitly these voltage sources, and we don't even show the ground node. It is all implicit now. We understand when we draw a circuit diagram like this that there is a reference node which is taken as 0 volts, and with respect to that reference voltage we have this node voltage as Vs1, this as V1, and this as Vs2. And obviously this circuit is much simpler to look at as compared to the original circuit, and that is why it is more convenient. Alright, now let us use superposition to obtain V1 in this circuit. What we will do is take Vs1 first, take Vs2 as 0, and what is the meaning of Vs2 equal to 0? That means this node voltage would be the same as the voltage at the reference node or the ground node. That means it is 0 volts, and that is shown using the ground symbol like that. And now in this case V1 is given by voltage division. Essentially it is the voltage between this node and the ground node, and this Vs1 is the voltage between this node and the ground node, and therefore we can use voltage division. So V1 is the voltage across R2, which is R2 divided by R1 plus R2 times Vs1, and that is our V1 in case 1. And similarly in the second case, in which we keep Vs2 but deactivate Vs1, that means we connect this node to the reference node, we get V1 as R1 divided by R1 plus R2 times Vs2, and that is our V1 in case 2, and finally we get the net V1 for the original circuit as V1 in case 1 plus V1 in case 2, and that is this expression, which is the same as the one we have seen earlier. We have seen that superposition works, at least for the examples we have considered so far. And now let us try to understand why it should be expected to work. And we will do that with the help of this specific example. But our findings are really much more general. All right. So here we have two independent sources, a voltage source and a current source. And what we will do is to take this node as the reference node. So with respect to that, this node voltage is Vs, this node voltage is V1, and this one is V2. And now let us write the KCL equations at node A and at node B. And in doing that, we will take current leaving a node as positive. So let us look at the first equation here. We have three currents at node A, this current, and this current. And what is this current? It is V1 minus Vs divided by R1. And since that current is leaving this node, that comes with a plus sign, that is this term over here. What about this current? That is V1 minus 0 divided by R2, the second term. And this current is V1 minus V2 divided by R3, that is the third term. And similarly, at node B, we have two currents, Is and this current. Now, Is is entering the node here, and therefore that comes with a negative sign, like that. And this current, which is leaving the node, is V2 minus V1 divided by R3, and that is the second term over here. So these are our KCL equations, and now let us see what we can do with them. Let us rewrite the KCL equations in a matrix form, and in doing that, let us use these definitions. The conductance G1, for example, is 1 over R1. Similarly, G2 would be 1 over R2, and so on. When we do that, we get this matrix equation here, and let us check that this first equation does indeed correspond to the first row over here. What is the coefficient of V1 in this equation? It is G1 plus G2 plus G3, and that is why we have G1 plus G2 plus G3 here. What is the coefficient of V2? It is minus G3, and that is why we see minus G3 over here. And this term, minus Vs times 1 over R1, does not depend on V1 or V2, and therefore we take it to the other side. And in doing that, it becomes plus G1 times Vs, and that is why we have G1 times Vs over here. And similarly, you can verify that the second equation here does correspond to our second KCL equation. All right. Now let us write this matrix as matrix A. So we have an equation of the form Ax equal to B, where x is our column vector consisting of V1 and V2, and B is the right hand side vector consisting of G1, Vs and Is. And from this matrix equation, we can obtain V1, V2 as A inverse times our RHS vector. So here is our V1, V2, A inverse times our RHS vector. Let us now write A inverse as this 2 by 2 matrix M11, M12, M21, M22, and let us bring this G1 inside this matrix now, and we do that by multiplying M11 and M21 by G1. So finally our V1, V2 is given by this matrix multiplied by this column vector, which consists of the two source terms Vs and Is. Now this column vector can be written as a sum of two column vectors, Vs0 and 0 is. And when we do that, we get this following equation. And now we should be able to see why superposition works, at least for this circuit. So this is our first column vector coming out of this Vs Is column vector, and this is the second column vector. And this first term is nothing but our V1, V2 in case 1, denoted here by this superscript 1, and this second term is nothing but our V1, V2 in case 2. In other words, the first vector, this one, is the response of the circuit due to Vs alone and Is deactivated, and that is why we have 0 over here. And the second vector, this one, is the response due to Is alone with Vs deactivated, and that is why we have 0 over here. Alright, now it turns out that all other currents and voltages in the circuit are linearly related to V1 and V2 because it's a linear circuit, and therefore any voltage, that is any node voltage or any branch voltage or any current in the circuit, can also be computed using superposition. And this is indeed a very powerful theorem, and we will find many uses of this theorem. To summarize, we have seen how superposition can be used in circuit analysis. In electronics, this technique is very useful, as we will discover later in this course. That is all for now. See you next time.